Assalamualaikum to Dr. Faiz and everyone. We are Group 7 and today we will present our project title CMOS Inverter Integrated Circuit using Cadence Virtuoso for the course BERG 4253 IC Design and Process. Our team consists of Nur Irdina, Nayli Najwa, Rania Iman Akhtar, Wong Chian and me, Nursyafiqah Izzati. Next, we move to our project. Our project aims to design and analyze a CMOS circuit using Cadence Virtuoso, a leading tool in IC design. Three key steps include design, which is creating a transistor level schematic based on IEE journal reference. Second one is simulation, which is evaluating circuit performance through rigorous testing. And the last one is analysis, where we're discussing working principles results and trade-off of the design. This study provides practical insight into CMOS technology, showcasing its application and limitation in modern digital circuits. We also demonstrate a full design flow from schematic capture to post-layout verification to ensuring the manufacturability in 0.25 micrometer TSMC technology. So next, I will explain about the IC design. There is two types of IC design, which is custom analog IC design or RF and digital IC design. In custom IC design, we focus on precision signal processing with critical specs such as gain, linearity, and noise immunity. It also uses continuous signals and require careful device matching and layout symmetry. The applications that include this design is wireless comms, biomedical device, high-frequency system, and it also enables modern electronics and technically demanding but essential. For the next type of IC design, which is digital IC design, is primarily implemented using CMOS, which is complementary metal oxide semiconductor technology and dominates modern computing system due to superior power performance characteristic. It is critical for computing hardware, memory system, and digital signal processing. It also encompasses all digital logic circuits, from basic logic gates to complex microprocessor and SoCs such as AND gate, OR gate. Next, for the application such as processor, memory, and DSP chips. Next, what we designed in this project, we created and designed the CMOS inverter, which include fundamental building blocks in digital integrated circuit design. It also consists of NMOS transistor and PMOS transistor. It serves as the basis for more complex digital circuits such as logic gates, flip-flop, and memory cell. It also involves creating a schematic, simulating its behavior, and generating a layout that adheres to specific design rules.
Today, I want to talk about the working principle of the CMOS. First, CMOS, the full name is Complement Metal Oxide Semiconductor Circuit, use PMOS transistor and NMOS transistor. PMOS and NMOS provide completely electrical characteristic. It enables high efficiency, low power logic function. In a CMOS inverter, PMOS connected between VDD and output. NMOS connect between output and VSS ground. So it will be in this form, it will become the inverter. And for the operation, input low means that is zero, PMOS is on and NMOS is off. The output is high. If the input high one in the NMOS means that it's on and PMOS off and the output is low. Only one transistor contact at a time. So it's very low question power and it's ideal for high speed, low power digital application. And for the next, it's completely complex circuits. It can you form to NAND gate, NOR gate, ring oscillator, use multiple CMOS inverter state. And finally, CMOS is the standard for integrated digital logic design.
Assalamualaikum warahmatullahi wabarakatuh and a very good evening. My name is Nayli Najwa binti Amiruddin and I am going to present about the methodology part. So the Cadence Virtual IC design tools in CentOS 7 virtual machine has been used for this assignment. GPDK90NM used for CMOS modeling. So here are the steps to perform the design. First, open the terminal and type Virtuoso N to start the Cadence. Second, create new library in Library Manager. Third, attach GPTK90 library to new library. Fourth, load library to ensure that the library is set up correctly, so make sure the library is successfully loaded. Next, create new cell inside the library. And last one, open the schematic view. So the design kit and technology files involved in this assignment. GPDK90 used to access CMOS device models and layout rules. Next, technology files defines design rules, layers and parameters. And last one, ensures compatibility across schematic layout and simulation. So this is the simulation and layout process. Design CMOS inverter using PMOS and NMOS. Use 2.5 volt DC and V pulse input. Output connected to 1 picofarad capacitor as a load. Pre-layout simulation in ADEL verified functions. Layout built using predefined GPDK90 NMOS and PMOS block. Connected using poly and metal. Design rule check DRC to fix layout errors. And last one, layout versus schematic check. So this is the project flowchart. First, start environment setup, send OS 7, launch Cadence Virtuoso, integrate GPTK and select GPTK90 technology, create library and schematic, which is CMOS inverter, perform pre-layout simulation, generate layout, run DRC and LVS check, perform extraction and post-layout simulation, and analyze results.
So this is the Cadence Virtuoso. First, we need to create the file, click New and Library, and enter your folder's name. I will go with Assignment and then click to attach to an existing technology library. Actually, I made the library already, so I will just click Cancel. Okay, now we need to open all the libraries that we have made in the assignments. We can see that it's schematic, layout, and symbol. First, we will open the schematic, click OK. The window will pop up. Now, we go to open the symbol library, which has been made. Then, we need to open the layout for the inverter. We need to click the Shift F to open the inside of the Cadence design, the PMOS and the NMOS. And we have another one to open, which is the executed value for the inverter. And here is the design, and just Shift F. This is the schematic diagram for the inverter CMOS, which we have the PMOS on the top and we have the NMOS on the bottom. But we need to change the symbol to be able to run the simulation via the inverter sim by using the ADL. Now this is the inverter sim, so to simulate this, we just need to go to the ADL, and for the analysis, we need to set the transient response for 6 micro and click moderate, apply, and OK. Then for the DC, we need to save the DC operating points. Component parameter, we need to select the VPOS and choose the VDC and click OK. And then we need to make the sweep range start from 0 to 2.5 volts as stated in our paper, and just click apply and OK. Now for the output, we need to edit and choose the V-in, V-out, and the VDD for this current as well, and just click apply and OK. Now we can start our simulation. So our simulation looks like this, and then right click and split the current strip to the trace, and then we can see for the V-in and the V-out and the VDD for the current, and this is our DC response. Once done with the layout drawing process, we need to go to the Asura and run the DRC check. Hit apply, OK, and now we can run the process. And then now we can see that there is no DRC error found. And next we need to check the LVS, layout versus the schematic. Hit apply and OK. Now we can see the run has been completed and no extraction problems were detected. So we will hit OK, and we can see the LVS run is completely successful. After done with the Asura DRC and LVC check, now we will convert this to the extracted value. As we can see here, I have already extracted the layout, and this is the final product. This is the inverter SIM for the ring oscillator. The concept is the same. Launch the ADL, click for the analysis. The transient response should be 500 nano. Click moderate and click apply, then OK. For the output, from schematic, we need to choose the output 1, output 2, output 3, output 4, and output 5. Once done, click apply and then hit OK. Then we need to go to the simulations, convergence 8, and set the initial condition to the output 5. Then we need to click apply, then OK, and we can proceed to run the simulation. Now we have run, right click, split the current strip and hit trace. Now we can see the output 1, output 2, output 3, output 4 and output 5 are in the inverted version.
Okay, hello, my name is Iman Akhtar binti Dasmim. So today I would like to present my part is advantages and conclusion. So the advantages is low power consumption, static. CMOS inverter draw almost zero static power except during switching because only leakage current flow when the input is stable. The second one is high noise margin. The sharp transition and full rail-to-rail output 0 to VDD provide robust noise margin, making it resilient to small voltage fluctuation. The third one is fast switching. The inverter switches quickly, especially with the sharp input ramp. PR equal to 100 nanosecond in the pulse source B2. The circuit includes a load capacitor C0 equal to 1 kF, simulating real-world capacitive loads and allowing transient analysis of propagation delay. The fourth one is simple design and analysis. CMOS inverters are fundamental digital building blocks, easy to model and simulate for timing, power, and performance. The last one is scalability. Easily integrated into larger logic systems like NAND, low bit and complex CMOS logic design. Second one is disadvantages. So for the disadvantages is the first one is dynamic power consumption. Power is consumed during switching due to charging or discharging of the load capacitor. The second one is short circuit current during transition. When input transition from low to high, both NMOS and PMOS may briefly conduct, causing short circuit current spike. The third one is speed degrades with capacitance. As the load capacitance C0 equal to 1 kF increases, delay increases and switching speed degrades limit high frequency performance. The fourth is not ideal for analog application. CMOS inverters are optimized for digital logic. Output levels are not linear. hence unsuitable for analog signal processing without modification. The last one is device mismatch and process variation. Variability in NMOS or PMOS sizing or threshold voltage can cause keyword switching points, impacting logic threshold and timing. The last one is the conclusion. The practical implementation of CMOS inverter and ring oscillator circuit using the Cadence IC design environment has proven to be both effective and educationally valuable. Through the complete design flow, including schematic entry, simulation, layout creation, DRC, LVS, and post-layout simulation, students gain hands-on experience in custom integrated circuit development. The CMOS inverter designed in 0.2 micro TSM MOSFET technology demonstrated current switching behavior during transient simulation, with clear output transition and expected rise and fall time. Post-layout simulation further validated that parasitic elements did not significantly alter uh, circuit functionality, confirming the design robustness. Building upon the inverter, a five-stage ring oscillator was successfully implemented using hierarchical design practices. The transient simulation of the ring oscillator confirmed periodic signal generation and the layout passed all verification checks, including DRC and LVS. This result confirmed that Cadence IC paired with the NCSC design kit provides a reliable and comprehensive platform for designing and analyzing VLSI circuits. The successful design and verification of both circuits illustrate the tool's capability to replicate real-world design challenges and outcomes, making it an essential asset for microelectronic education and prototyping. That's all from me. Thank you.